We're going to start now. As usual, we're a little late, and I'm just going to briefly introduce Genspace for anyone who hasn't been here. I see a lot of familiar faces. Hopefully, a lot of you know about us already. We're a new type of entity. We're called a community lab, and what that means is that we were formed out of the community. We didn't come out of an institution or a corporation. We're a not-for-profit, and we exist because we believe that everyone should have access to information about, and more importantly, hands-on access to new biotechnologies. And this includes everything from, modern DNA science, personal genomics, things like that, synthetic biology, to this trend now to use biomaterials instead of synthetic materials, things like mushroom mycelia as building material, or bacterial cellulose as clothing, perhaps sustainable design. And we give courses for the general public. We have lab memberships, which for a pretty low price point, $100 a month, you can come in and use the lab for a project of your own. The other thing we care about is it's safe. But we don't make any judgments as to whether we think it's a crazy project or a good project, or if it's going to succeed or fail or make money or save mankind, just as long as it's safe. We're pretty much okay with it. We run student events. We had one of our former iGEM team members is here, the International Genetically Engineered Machine Competition. So we have events for students, and we also curate various art science events, both internal and external. This is part of our talk series, and we've had everything from artists that see history through the eyes of animals to scientists working with nanotechnology at the smallest scale possible. So our talks really run the spectrum. We are not-for-profit, so there is a donation box here next to the food in case you're interested, and we appreciate it. And we are very, very happy today to welcome this really extraordinary team of people that won this prestigious award from NASA, and I'm going to let Carter, our Director of Outreach Events, introduce them.
Thank you. Welcome to Genspace, and welcome to this presentation event tonight. This is most likely, or at least for some time, the last event that I'm involved with, because I'm going back to Spain, going back to Barcelona on Thursday. I've been a volunteer at Genspace for nearly 2 years, year and a half.
Oh, more than that.
More than that. And it's been amazing working here, and my idea is to bring back all these good vibes and knowledge and this sort of biomaker space model back to Spain, back to Barcelona, Madrid, and maybe other European cities. And I would like to, of course, stay and keep collaborating with Genspace and probably organize events on both sides of the Atlantic Ocean if we can.
I want to go to Barcelona.
And of course, everybody's invited to come to Barcelona. Well, the story starts like many other stories. Here in New York City, you come across amazingly talented people all the time with amazing projects. And my friend Sumiko, who is also a very talented singer, she's here with us. And she invited me to a dinner, and I met a group of very talented architects during that dinner. And I found out that they did these amazing projects about building a house on Mars. And they presented this project to NASA, this international contest. And well, they presented something amazingly innovative and different and radical and beautiful. And they won this contest. So immediately I was asking them would you like to come over to Genspace and present this, see what we can do out of an evening around this topic? And hopefully, maybe this has future activities related to, space architecture or terraformation, astrobiology, and so on here in Genspace in the future. I will let the speakers present themselves and talk about this amazing project. I think the way it has happened, the way it has been developed from my conversations with Masa and colleagues, it's amazing the way that they found solutions, and the whole process behind it is incredible. And I would like to make this sort of a bit of a dynamic, more dynamic and engaging presentation. So, it would be, if you guys have questions during their talk, there's going to be questions at the end of the presentation. So there's going to be time for that. But if there's specific questions directed, very much to do what is being said at the moment, feel free to raise your hand and to ask those questions. And I hope everybody enjoys this for sure. Welcome, guys, and thank you for being here. Thank you.
Thank you for inviting us here to Genspace for this presentation. We're a group of actually two groups. One group is called SEARCH, which is Space Exploration Architecture, composed of 5 individuals. Jeffrey Montes is here, Kelsey Lents, Michael Morris is here also, and then Melody Yashar and Christina Ciardullo are not here, but they're here in spirit. And then the other side of the group is Cloud's Architecture Office, which includes myself, which is Hustad, Masa, and Yuko. And there will be like a credit screen, so I can show you more formally the kind of team structure. I just want to start, I guess, in the spirit of kind of the open dialogue, asking you guys a question. Has anybody seen this project before? If you could raise your hand. Good. Can everybody see the image, or should we kill the lights?
Maybe
Kill the lights? Is that possible?
Yes.
Great. Okay. So I'm going to start with an introduction, and basically we've broken the talk into chapters, and each of us will cover a chapter. So I'll basically introduce the framework of the competition and some background information about Mars, which is the context for this project. NASA teamed up with America Makes, which is a 3D printing trade group. And to help hold a design competition, which is run from May to September of this year. And they stipulated these requirements on the left-hand side and the judging criteria on the right-hand side. So essentially, the requirements were for Habitat to house a crew of 4 astronauts for a duration of 1 year. They gave a size, like 1,000 square foot footprint, which is basically driven by the environmental control system. So the oxygen and CO2 scrubbers can only manage a certain volume. And they gave us a kind of general program, including hygiene areas, bedrooms, cooking areas, etc. And they stipulated that we should use 3D printing involving indigenous materials. So the motivation behind the competition is that it's very expensive to bring material into space, right? So if you can minimize your payload and use what's there as much as possible, you're like miles ahead. So using 3D print technology, which is sort of a recent phenomenon, they asked the entrants to come up with a 3D printed habitat design. So this is a team, as I mentioned, is composed of 2 sort of distinct entities, Search and Cloud's Architecture Office, as well as a a whole cast of research consultants, including planetary geologists, structural engineers, which are here in the city, Leslie Roberts and Associates, radiation specialists, a whole cast of characters, and they all kind of had their input at various points throughout the development of the project. So the context, the site itself. Mars is in some ways similar to Earth, and in some ways it's very different than Earth. Its atmosphere is much thinner than Earth's. It's about 1/100th of Earth's atmosphere in terms of the density of it. And the composition is quite different. It's primarily carbon dioxide, where ours has very trace amounts of carbon dioxide. The pressure is also quite different. It's like a near vacuum kind of environment. In terms of the sun, Mars is about 1.5 times as far away from the sun as Earth. So the amount of solar flux, like solar energy that's reaching the surface, is 40% of the Earth's. So using solar energy is a little bit more challenging. You need more surface area to get the amount of solar power. Their day length is very, very similar to ours. It's about 40 minutes longer than our day. And the year is about twice as long. So because the orbit is further away, it takes longer for the planet to circle the sun. The size and gravity, it's about half the size of Earth, and the gravity is about 1/3 of Earth. So you can essentially jump 3 times as high on Mars as you could here, and structural members can span longer, and you can use lighter weight framing material, let's say. Additionally, the axial tilt, the obliquity of the planet, is very similar to Earth, which means that Mars also has the seasons of Earth. Except their seasons are actually twice as long as ours, so because of the longer year. The distance is significant, so getting there is a challenge. Actually, you have to kind of time your departure and return in terms of the alignment of the planets, the orbits of the planets. So a typical mission might be 2.5 years, which involves about 6 months to get there, a year on the surface, and then 6 months to get back. Mars itself has some of the most extreme topography in the solar system. It has the highest, biggest mountain and the deepest canyon. These little travel brochures are made by SpaceX. They're planning to put 1 million people on Mars within 20 years. This is like a roughness map of the surface, so like the terrain roughness. And because the atmosphere is so thin, the surface is exposed to radiation. So you get bombarded by solar radiation and cosmic galactic radiation. So basically, I think they're saying that the first meter of the planet is basically sterile. And as well as comets, so the surface is pockmarked with craters. The surface is also covered by a layer of dust called regolith, which often get kicked up into large dust storms, which at times can cover half of the planets or even the full planet, the full face of the planet, which is another challenge for solar power. The temperature range on Mars, these are the extremes, so you'll get -133 Celsius on like a polar winter, so on the extreme poles in the wintertime, that's a low temperature, up to 80 degrees Fahrenheit or 27 C, which is in the summertime at the equator, so it's quite a range. And these are temperature maps of the surface, and at the bottom you can see, on a December day, what the range would be. It goes from -125 to 20 C, like the red is about 60 degrees or so. And then these are also like the September days, like the daytime and nighttime, so you can see the radiation on the same day. Water. So this competition took place before the announcement of liquid water on Mars, but we already knew that Mars has significant amounts of frozen ice water, to the extent that if you melted all of it, it would cover the surface of Mars to a depth of 10 meters or about 30 feet. so this is a visualization of ancient Mars, like if all that water was actually liquid. It's hypothesized that there are large seas, large oceans on the surface. And that chart on the right-hand corner shows the progression from 4 billion years ago, 3 billion to 1, and now. So basically the water, because the atmosphere disappeared, the water was sort of trapped in the ice of the poles. In 2008, we sent Phoenix, which was a lander. In Phoenix, when it landed, the thrusters blew away some of the regolith and exposed ice. And so then they took a shovel from Phoenix and kind of started digging, and this is what they saw. They saw water ice just below the surface. And the right-hand side, you can see the rate of sublimation over 4 days. Like the sol is actually 1 day, so you can see that the ice has disappeared over 4 days. Some more data maps. The left-hand corner is the hydrogen abundance, which is assumed to be like a water equivalent. Red is the high concentration, so most of the water is at the top and bottom of the planet. This is a perchlorate distribution map, which is one kind of side note is that some people believe that the regolith is toxic, perchlorate, when it's inhaled by a biological life form, it causes a lot of problems. And then the silicon distribution, silicon can be used to make glass. And then a dust index, so this is kind of the dustiness of the planet. Using these kind of maps and overlaying the different criteria, the different data of the various characteristics, we were able to kind of hone in on a site. This happened later on in the process, once we kind of had an idea of what we were doing. But we chose a site that's in northern latitudes, close to the pole. A little bit below the Phoenix landing site, so that image of the kind of exposed ice, that's a little bit north of our site. So the site is called Mons, and those are the kind of latitude and longitude of it. This is a kind of an idealized site plan showing the habitat in the center and distribution of the power array, the communication center, and the cache for food. And then these are landing ellipses, which I don't know if you know, but to actually land a payload on Mars, there's very little accuracy. The window or the footprint of the landing is about 4 kilometers by 12 kilometers at the moment. Hopefully in 20 years' time, they'll be able to kind of focus that footprint so we can get more precise with the landing. But the other key component of this is access to ice. So the gray areas are seen to be subsurface ice deposits, which will need to be nearby. Another criteria that we looked at is planetary protection, which might be interesting to some of you if you're biologists. In 1967, there was an outer space protocol that was signed by 104 nations agreeing to essentially protect celestial bodies, meaning that we can't contaminate them with our own biological material. So the top left is an image of the Viking Mission from the 1970s, and they essentially baked the spacecraft at 120 degrees Celsius for 30 hours to basically kill all the spores and bacteria on the spacecraft. And then, of course, within the mission, you have all kinds of detritus. So that's the surface of Mars. Those are like shields and fairings that drop off during sort of delivery of payloads. And then this is on the moon, where like an old probe is being visited by a new kind of visit from the Apollo team. So you can see the Apollo spacecraft and how close it landed to the old probe, and they sort of came up to the pictures. And what we know is that probes have bacteria on their surface, and so they limit the spore count to 300,000 spores per craft, or about 300 spores per square meter, in terms of what you're allowed to bring to a celestial body, another planet. And when it comes to a manned mission, it's a whole different story, right? Because people are just bacteria bags, basically. And so this is a spacesuit with all of its various moving parts and joints. There's something like 30 different joints, and they all sort of leak inevitably, and space is also bent because when they build up pressure, they need to release various gases. So this image in the middle is actually from Apollo 12, and it's one of the few images where you can actually see the kind of mist and vapor of the venting of the space into the kind of lunar atmosphere. So suits leak and also habitats leak, right? So they also need to balance the gases and the pressures inside, so they're going to have to be able to vent and leak their environment to the outside. Some of the precedents that we looked at from the 1960s and primarily the 80s, these three are from the mid-80s when the Bush Senior, no, it wasn't Bush Senior, but there's a lot of interest in going to Mars. And you can see that there's kind of a common element with them that they're usually sort of spherical, underground, partially, and also they have inflatable components. And these are kind of updated, more modern versions of prototypes that we're looking at now. Again, it's like an inflatable kind of pressure volume without windows. And this one is actually intended for Mars, where they have a rover that docks right up to the habitat, so you don't actually have to go outside to get into the rover. This is the European version. Again, no windows. And Mars One, which is a private venture, and essentially it consists of the transit vehicles, which are the capsules. They would just actually be landed and sort of somehow arranged into this neat line and hooked up. So you're going to end up living in your transit vehicle, although they do have plans for extending them. And this is maybe the most current and sort of updated version of an outer planet habitat. This one's on the moon, and it's by Norman Foster, which is a European architect. And it consists of a module, a landing module that then is inflated. Part of it is inflated, and around that sort of inflated dome, they essentially just kind of cover it in regolith, like 3D print regolith around it to create this protective shell. And the interior again is windowless and dark. Basically, what we found is that most of the habitats are cave-like, without sort of a connection to the landscape and without access to natural light. So out of this kind of research, we developed basic design criteria. The meta requirements are what came from the competition. Using indigenous materials for a crew of 4, autonomously constructed, etc. And then we also added our own sort of architectural criteria. Because this is sort of, it could potentially be the first piece of architecture around Mars, we felt that it needed to be iconic and have celebrate the human presence on Mars, to have some kind of cultural value, right? Some image that can people can identify with. Also, the architecture should provide visualized stimuli using natural light or changing color. It should also allow for changing imagery. So if there's a window to the landscape and the landscape is changing, that satisfies the criteria. It ensures crew safety, and also we wanted to protect Mars from contamination of humans, right? Forward contamination. As well as establishing vertical orientation in the landscape so that it has some presence in the Martian landscape, something that can be visible from a distance. As well as having a variety of spatial qualities. So from common areas where the crew would get together and eat to their own private quarters, and then these sort of also in between spaces that are like a kind of intermediate zone that is not programmed, that they can actually go and sort of unwind. And throughout this kind of criteria, there's a psychological factor. When people go to Antarctica or like into submarines or to kind of these long, deep missions, it's been found that actually the most kind of difficult criteria is the mental criteria, the kind of psychological factor. And so, when you're spending 6 months in a capsule and you arrive on Mars, we wanted the crew to be able to sort of unwind, to be able to stretch their legs, to kind of walk out and kind of stretch out a little bit. And that kind of sort of more normative connection to the landscape, like we have here, like kind of being able to walk out to some degree and look out to some degree, is what we felt was really the value of the project that kind of distinguished it from the kind of precedents that we were looking at. Yeah.
Okay, so next chapter is kind of architectural design process. And when we started discussing with Ricky about this presentation, first thing he kind of mentioned was he's very interested in the kind of process or the thinking behind it. So we thought that was great. And nowadays everything you think is on the web, but actually like those kind of process behind is typically not in the web. There's something special that we can present to you. And also we thought we're going to bring some process studies and sketches that led to the final solution. So anyway, there goes, and welcome to the last stage, the architectural design. So when we started the kind of initial sketches, just 8 of us just brainstorming, gathering, and showing ideas, discussing. So this was some of the sketches that came out in the initial stage. And we have to confess that we started with the regular structure, like president, the ideas post-up presented from the past. So that was our departure point, and so these sketches, for instance, it is different from what we ended up at the final solution, but there's a lot of ideas that led to the solution. So for instance, this is like also was mentioning, one challenge is to how you shield from the radiation with very strong, and you need very hefty shield if you use regolith. And we're also interested in how we kind of integrate into the landscape or the sun orientation, including wind direction and so forth. So that was one idea to fit into the context of the landscape. And we're also very interested in internal aspects, human kind of aspects. So this was idea of having a hydroponic garden in the middle that would obviously physically create oxygen and so forth and food, as well as raising plants and seeing green, very good for human psychology. And something like this, very minimal, simple, very iconic silhouette or form that stands out in a margin landscape, that there's no man-made structure. And this is more the vertical idea of the vertical volume in the landscape. And this is kind of using the regolith as a foundation, but the habitation area is actually inflatable element that kind of weave into the regolith structure. And the one big, among these ideas, one big idea we really wanted to achieve was something view to the landscape, this amazing margin landscape. And both physically to gain natural light for not only for energy purpose but also psychological well-being of the astronauts. Because the cycle of the Mars is actually very close to Earth, 40 minutes different. So using the natural light for human, the cycle is very helpful for the health of the astronaut. And the other idea was this kind of a layered space idea. You can see the habitation here, and then there'll be like a buffer space that between the outside, very harsh environment, and human space. So you're not right next to the harsh, the outside space, but there's a buffer space that helps both directions, meaning that what I mentioned that the concern we don't want to pollute the Mars. So we can control the elements that bend out from the habitation area into this intermediate space before it cuts. And then also, as a psychologically you're in this, but there is a space in between. That's either kind of not inside nor exactly outside. It's in between space that would kind of buffer you from psychologically, buffer you psychologically from the outside space. The biggest challenge was the radiation, because it's how do you kind of shield the radiation at the same time, creating this big opening, natural light and so through our research, we found out that actually water is one of the most effective shielding material for radiation. This was done, test done in International Space Station. What they used was a wet tissue, like a napkin, wet napkin. They bundled it up like 6 centimeters and then did a measurement for the radiation. This is the results. The red is actually with the tissue cover, so it dramatically reduces the amount of radiation compared to without. So we thought ice has amazing potential, with it is so much ice on Mars. It's an indigenous material we can use, and then it's a source of life. Wherever we go, we have to have water anyway to survive. So it's going to be there no matter what. And then it's a very effective radiation shield. And also it transmits natural light and potentially a view out as well. And the natural light will also help for the plants inside, for the garden. And it also makes sense to think of ice because the average temperature of Mars is like below 43 Celsius below zero. And it is very energy efficient in terms of creating ice, so you don't have to use high electricity energy to create for instance, sintering the regolith or creating metal from the regolith and so forth. And lastly, it is a very natural material with kind of an aesthetic to it. It's a very beautiful object as well. But another challenge was, okay, so we're going to use ice, but problem is ice on Mars is something, it's like a dry ice on Earth. Because of the low temperature and atmosphere, it sublimates from ice to vapor. So there's once you expose the ice, it basically evaporates. So how do you create the shelter or shell using ice? So through our research, we found this study done by a Romanian engineer called Stefan Har. And his concept was very interesting to us because he was studying about creating a shell in outer space, basically using sort of transmission of a water chemical stage and using the vapor of water as a medium for basically three-dimensional 3D printing. And for instance, there's if you pressurize a certain volume using transparent films such as ETFE to the high strength, UV resistant, transparent, inflatable volume, then once you inject water vapor with just sublimation effect, with the fan, the help of fan, it will gather to the inside surface of the volume, and once contact with the outside temperature is so low, it will start freezing. And so it's not a conventional 3D printing like layered stacking, but it's actually like a real 3D in a sense, the additive manufacturing. So we thought that was a great concept and tried a bunch of studies. And this is just part of what we do. We have tons more of these, but I can't show everything. But just wanted to show a little bit how we work. We just come up with a bunch of ideas as much as possible. And the thing is, I think a lot of times, great idea comes from really dumbest beginning point. And because what's most exciting to us is when we come up to a solution or design that's very unpredictable. You can predict the finished product from the beginning of design. So we try to come up with as much of ideas and find a very right solution that's not predictable, unpredictable. So this was first submission, but the competition was in 3 stages. So this was the first stage. we had sort of a low profile, asymmetrical volume with this is a landing element, lander, that comes first with the stuff inside these materials, the membrane, the printing machine, and so on. And then we have basically two layers. The first layer with the ice, the outside, the shielding. Then another inside layer for the habitation area that is insulated, so it's warmer. And in between space that we mentioned before, and the hydroponic garden in the middle. So it had a redundancy effect that you're protected by kind of 3 layers under the inner shell and outer shell. So after submitting, we kind of discussed with our engineers and scientists to develop our project. And first thing they told us was the form, asymmetrical form, is not very efficient. That's what they, that's how they think, but the engineers very concerned about the efficiency. So that was one thing, and but that was our scheme. This was their switch. But we wanted to, as I mentioned, we wanted to achieve kind of iconic, really identifiable, kind of asymmetrical kind of volumeter spirit, basically. So we went on to study more with somewhere in between, not freeform like the first one, but not completely symmetrical like that one, but somewhere in between, using a cone, the composite of cone. So it's essentially still a platonic geometry, very pure form. But at the same time, we compose so there will be a direction to the space. And these crease lines that emphasize the asymmetry direction. So out of these, we kind of picked, or more, but we picked the simplest one, essentially. The kind of shard-like form that jet out from the ground. So this was for the second submission, second stage. So here you can see what we did was we rotated the lander so it's vertical, which we found out through research that the lander makes sense. The inside actually vertical configuration. So this gave us the opportunity to have this the height of the landmark. And then the lander is completely contained in